the way. All right. So thank you very much for attending my presentation on some new ideas of integrating RooFit more in the Python ecosystem. And this time I will talk about bridging RooFit and SymPy, which is a mathematics symbolic mathematics library in Python, a bit like Mathematica. So you can use it to build expression trees, and I'll show you how you can then evaluate them as RooFit probability density functions. So in my talk, I will give you a brief reminder of what RooFit is and what it can do in its fundamental feature set. Then I will also remind you of the existing interoperability between RooFit and Python libraries. And then I get to the new stuff. Yeah, so I will show some improvements on the way how you can define your custom PDFs on the fly, and especially with an application of taking these expressions from SymPy computation graphs. And finally, I show a little toy example where this is applied in amplitude analysis. So I'm sorry that this notebook was not submitted on Binder, actually, because well, you have to use root master to run it, unfortunately, and there was no way to get that to work. So so if you would source root master from CVMFS from the Nightlist, then this whole notebook should work, at least tomorrow. Okay, so to remind you what RooFit is, so it is part of the root C++ software framework. It is a library for statistical data modeling. And the classic things that you do with it is build a statistical model from a set of modular C++ classes. And then you can use this model to, for example, optimize, do parameter estimations or sample toy data. So let's just show again the little hello world of RooFit. Just to set the stage here a little bit. We'll just import root and make sure that the notebook will not be too verbose here. And so nowadays people often use this Roo workspace factory language to define their models. So we do that too here for this example. It's like a domain-specific C++ oriented language that allows you to define your RooFit objects. So let's define a Landau distribution, a Gaussian, and then the convolution of the two. And then finally, we can do like what you often do when you have a model. You sample some toy data from it and fit this model to toy data, just to get a feeling for this model and how the fit would converge. So yeah, and then so we see here in this example, the fit was converging successfully with this status 0 for Minui 2. And then finally, another thing that is supported in RooFit is plotting both your data sets and models. So we'll briefly do that too with our toy model here. So there you see here the sampled toy data set, the Landau, and the Landau convoluted with the Gaussian that might represent some resolution function, for example. Okay, so that was a reminder on RooFit in general. And we already have some interoperability functions exclusive to PyRoot that you can use, for example, to import and export RooFit data sets to NumPy or Pandas. So here we just use this toPandas method to export the data set to a data frame. So that's the toy data set that we sampled before. So you can find more tutorials on this, but I think I talked about this already before. This is just as a reminder about what interoperability features already exist in PyRoot. So today I wanted to talk more about defining custom PDFs. And in RooFit, you usually have 3 ways to do that. So first, you implement your own C++ class, basically, that inherits from the RooFit PDF base class. where you override the relevant functions for the evaluation. So that is a bit more advanced, huh? And you cannot do that interactively in a notebook. What you can do interactively in the notebook is to use this other class. It's this generic PDF class, or this expression operation in the workspace factory language, to just in time compile some C++ string here and use it in a RooFit PDF. So this is done with the help of the root interpreter under the hood. I think people generally use this quite a lot. So this is probably the most common way to define your own PDF. But finally, there's a third option that looks similar to the second one, in the sense that you specify your PDF with a custom string, but actually the code is not just in time compiled like by the interpreter, but it's actually dumped to disk in some files and then compiled with what we call in root rclick. It's some other tools to actually invoke the GCC or whatever compiler you have to then generate the shared library on the fly and then include it with the interpreter. So because of all these steps involved there, it takes a bit longer. We'll see that now. It's still running the cell. But in general, it's more flexible than the second approach with the root generic PDF, because you can also customize the code that is written out by this class factory afterwards, or you could even share these generated source files with colleagues. But what do you do if the expression becomes more complicated? Like, I mean, that's what we saw on the previous slide, was just a simple example of a Gaussian with sigma equals to 1, so not very complicated. And you don't necessarily want to write everything in one big string. So you could then go the usual RooFit modular way and build your top-level PDF with some RooFit mathematical operator classes, like the RooAdd PDF for the addition of several PDF components. But an alternative approach that I see became a bit, kind of popular today is to build the expression tree with a separate library, for example, SymPy in Python. And then you could import the generated expression in RooFit if you want. So let's see how this would actually work. Huh? Let's import some usual stuff like NumPy, Matplotlib, and also SymPy. So in SymPy, the basic variables are called symbols, and you first have to define them before doing some operations with them. So let's define one symbol for our observable x and one for the parameter mu, and try to rebuild the same simple Gaussian model as before. So let's go. We do this a bit like in NumPy, but for the mathematical operations, you use the SymPy functions. And what you get out of it is not an evaluated expression, but is an object that represents the expression. And if you print this in the notebook, it actually gives you a nice LaTeX representation of the formula. Okay, back to RooFit world. So now we have this expression in SymPy. So I should mention that you can do lots of things with that. You can, for example, export it to TensorFlow compute graphs or to JAX stuff, whatever you call it in JAX. I'm not that familiar with it. Or you can export it to simple C code. Let's do that now. Naturally, the code doesn't look so complicated, but we can then take this C code and give it back to our RooFit class factory and define the Gaussian again, like similar to the third bullet point I was showing some slides ago, but this time we take the expression exported from SymPy. Okay, let's go print the workspace. There we see there is some automatically generated PDF class here that represents a Gaussian with a sigma equals to 1. Just to show that you can use these objects as regular RooFit PDFs, and also to show another new feature in RooFit. let's see how you can use this PDF then to generate a likelihood object, so a new object that represents a likelihood for a toy data set. So in RooFit, you usually do this with this create NLL method. That is a method of the RooApps PDF base class. And as of Root 30, 630, which will come out in a few weeks, there are few backends that you can actually select for this likelihood evaluation. So in the a bit like I guess PyHF has either JAX, PyTorch, or TensorFlow as a backend. We also have a few backends here. So, for example, the old backend that was there since the beginning of RooFit, then a new vectorized CPU backend, a GPU backend, and now another backend that we call the code generation backend. And this one actually generates a simple C++ code for the NLL object on the fly, wraps it back in the in a RooFit object that you can use as usual. But the cool thing about it is that it actually also generates the code for the gradient and compiles it on the fly with the CLUD compiler plugin. So that's what I wanted to show you here briefly in passing. As you see, it's quite experimental, so you get a bit more warnings than you would usually like. I'm sorry for that. And but then you can see that actually from this likelihood object, you can not only get the values out, which we now here do in this example here for a linear space of mu values to do some likelihood scan, but you can actually also get the gradient of the NLL. And here it will actually use internally the generated gradient code with the CLUD source code transformation AD tool. So nothing really surprising here. The likelihood looks Gaussian and the gradient is a straight line. So that was just a aside. And now finally, let's see if this approach can actually handle some more complicated formula. So that what I showed there was a pretty simple SymPy expression with a simple Gaussian. But in a real world use case, you would use this for example, for amplitude analysis, where you generate a super complicated expression that considers the interference between different amplitudes, and you really cannot use any custom RooFit classes. You cannot use stock RooFit classes anymore in many of these use cases because the formula becomes so complicated for the intensity. So building your custom PDFs and expressions is quite common in amplitude analysis, I think. And so to show how this would scale, this code generation approach with SymPy, let's use the quite nice Q rules and MForm packages from the common partial wave analysis project to build an expression for a complex amplitude. So here we are defining the reaction for the decay of a J psi into a photon and two pi zeros. So, I mean, this is mostly code I copy-pasted from a ComPWA tutorial, so I will not explain you more than about it. So, but it can do quite nice things here. You can then also visualize this reaction here with GraphViz. So there you see that the J psi can decay to this finite state via some resonances, and they're all considered in the amplitude, and that's why it's a really nice, complicated expression that we can try RooFit on. So this block is actually building the SymPy expression. And but it still contains some integrals that are not evaluated by default. So to get a really closed form expression, and like we had in the simple example, you have to call this doit function here, and then you in principle get the expression that you can then print in LaTeX again. But I'm not going to do that here. It actually crashed my notebook when I tried to do that because it's so big. So yeah. Try that only for at your own risk. And so finally, just to get back into RooFit world again, once again, we need to massage this expression a bit, because all the variable names or symbol names, as they're called in SymPy, they for RooFit they would have to the names would need to be valid C++ variable names, otherwise it doesn't work. So I have some dictionary to replace symbol names. It's a boring part of the code, so I don't show you how I create this replacements dictionary. You see that in the full notebook, but I skipped it in the presentation. So what is important now? If you see now the free variables of the SymPy expressions, or free symbols as it's called in SymPy, then you see some names that look like they can be digested as C++ variable names. Okay, now let's get the code again, the C code. And let's dare to print it out, at least the first 2000 characters. Okay, it looks already like it's a quite complicated amplitude. And what I want to highlight here is that it actually, it uses complex numbers. I don't see it right now because it's quite long. Now, here, for example, so there's this capital I, which is actually the imaginary unit. So this is in fact a complex expression. So in total, this would be like 10,000 characters long if we would print all of that. And so that's another thing that you can now do with Root 630. So these Roo class factory, it actually can digest now these expressions with the imaginary units. Before that was not possible. Okay. So let's get our workspace again, as usual. So we create now a new RooFit workspace with the observer builds here. So these are the relevant kinematic variables for that final state there. So the parameters, we also create them as a RooFit object. We do this with the information that we have from the SymPy expression. So this is some dictionary with these new parameter names that I talked about before. The details are not that relevant again. But now to the interesting part. Let's create this on-the-fly compiled PDF object and then instantiate it with this big code that we exported from the SymPy expression. So takes again some time. Some new thing here, by the way, is if you run the cell again now, in the previous root versions it would have crashed, but now it remembers what classes it actually already compiled, and if you run this again, it will not take any time anymore and also not crash. So let's import this custom PDF into the workspace. And just to make it a bit more interesting and show how we can actually use these custom PDFs in the Python, in the RooFit ecosystem, let's once again do the convolution of this custom shape with the Gaussian resolution function using the fast Fourier transform. Okay, now the workspace is set up. It contains quite some stuff here, and most importantly, the custom PDF here, the resolution function, and the final convolution. And so now let's do the exercise of toy dataset generation and plotting again. I have to warn you, I don't think that the actual dataset we are sampling here is physical, because to do the phase-based sampling correct with the good constraints to not have divergences and so on, you have to do a few more things in the with the tools in the ComPWA ecosystem, but we're not going to do that. I mean, for the sake of this tutorial, I just wanted to show you that RooFit can digest super huge SymPy expressions, so we don't really worry if it's physical or not. let's just sample the data from the shape that we have and look at how that would be in the plot. So we see the line shape is actually quite complicated. And so the dashed part here is without the convolution, and a solid line here is with this convolution here. So you can also fit it. It takes some time now because this expression is not easy to evaluate for the computer. And unfortunately, you can't use the new code generation backend yet either to speed things up for the gradient because it doesn't support complex numbers yet. So that's something to come. So the result seems to have converged, and the parameters have reasonable values if you compare them to the actual names of the resonances there that are in the variable names. Okay, so in conclusion, I think SymPy is quite useful for defining complex expressions in our increasingly complicated physics analysis, and it's nice that you can export these expressions to different frameworks, therefore to different evaluation backends like TensorFlow, JAX, or even C for use in the RooFit context. RooFit can actually deal with these very complicated expressions. So, and then you can just take whatever suits your needs and mix and match tools according to your preference, I guess. Possible next steps. So we could also extend this root class factory to generate CUDA kernel code so that you can then also use the CUDA evaluation backend with these custom PDFs. And maybe there's also the possibility to make this interface a bit more Pythonic. That's it from my side. Thanks for your attention. And whenever you have any input on this, feel free to reach out to me also later, or if you have any ideas.
Thanks so much. Quite impressive, actually. I already see one hand, so I'll give the floor to Alexander. Alex?
Hi. Yeah, thanks. This is really cool to see. I'm curious a bit how you see this relate to HS3, because here effectively SymPy sort of defines a way in which you can like define an expression, which then you can export to C and then go to RooFit. And I guess from there you could go to HS3, but you can't go the other way. And I'm wondering if there's some way to sort of like do the SymPy to string back and forth type thing, or like some way to standardize around one way of doing the expression, which you can now go in any direction. Because I do think it's like super cool to have SymPy give you both like essentially things that you can compile as well as like LaTeX and everything, but I don't know how it relates and like might connect to HS3.
Yeah, it might, absolutely. So the challenge there is that HS3 comes mostly from the CMS Atlas community now and is oriented towards the bin template analysis. So as you see, these expressions in amplitude analysis, they can get quite complicated, and we really have to probably go back to the drawing board at some point to also cover these use cases. So to give the short answer, I don't see an easy way to connect this work to HS3 for the moment. But in the future, it might be relevant once HS3 has established itself in the bins analysis environment.
Okay, Alex, any other questions? Otherwise, I would have an opposite one, which is often for these kind of developments, you do it because you have a use case, or so. In your case, are you working together with somebody doing an amplitude analysis, or this was coming out of interest, a personal interest, something like that?
No, this is because I saw at SHEP earlier this year quite an interest in amplitude analysis, and I thought there are some nice ways in which we can maybe connect the different frameworks to do that a bit more in an easier way. So I was in particular impressed by this ComPWA, And yeah, as have seen today, actually the work on the root side to integrate this SymPy expression handling is not that far. So it was mostly, you know, I mostly tried to do a few things and now solicit feedback from the community also thanks to PyHab, and then see if there's actually a use case for that and continue development.
I see. Thanks. Yeah. So I guess, yeah, you mentioned ComPWA. Yeah. So I guess you are in touch with Remco and maybe even Jonas for ZFit, because I think they are collaborating on some aspects actually for amplitude analysis.
Yes, exactly. So we are in contact, and if you can then use these same expressions and with different fitting tools, this would also make nice benchmark comparisons, for example. So that's another reason why we look into this.
Yeah, fair enough. Yes. So Alex has another question. Go ahead. Thank you.
Right. Yeah. Thanks also for the other answer, Jonas. I had another question because you briefly showed derivatives here. And I was wondering about the scope of what kind of derivatives are supported. Is the scope currently likelihoods with respect to parameter? Is this broader than this? Can I do things with respect to global observables and such? What's in scope here?
So right now it's still hard coded that the gradient is with respect to all three parameters in the model. So that's something that we will have in the next root release, I guess, a more general way to define the direction of the gradient with respect to which parameters you want to get it, and then that would also include global observables. So that's something that we can do, but probably to the very complicated stuff like differentiating through the minimization, that will take much more time to get to that.
Okay, very nice. Thanks.